Quantum theory is the most important discovery of the 20th century. And it has been presented to the public in a completely distorted way. What you hear normally has very little to do with quantum theory. The quantum theory made it possible to understand atoms. And of course, atoms make molecules, and thereby you understand chemistry, the chemical bond. And chemistry, in turn, is the basis of biology. One of the things that quantum theory permitted to understand was solid bodies, and thereby the conduction of electricity in solids. That theory was started by my teacher Sommerfeld in 1927, the second year of my presence at his laboratory. And he and I wrote a comprehensive treatise on this subject 6 years later. Semiconductors are a special kind of solids which are insulators when they are pure, but you can put some specially chosen impurity in them, and then they become conductors. Now, these semiconductors can then be used to make transistors, which are one of the devices based on quantum theory. And transistors are in nearly every gadget that you have, certainly in every radio, in every TV, and in many other devices. Transistors rectify currents. When you get a radio or TV signal, it's an oscillating electric field, and transistors rectify it, that is leading then just a direct current into your apparatus. Transistors replaced vacuum tubes. I suppose most of you are old enough to remember vacuum tubes, which were the predecessors of transistors. And this room full of vacuum tubes has been replaced by a small wafer, maybe the size of your thumbnail of transistor, where this wafer contains what is called a printed circuit, and in the printed circuit are lots of transistors which replace the whole room full of vacuum tubes, which precedes it. This is just one of many technical inventions of the last 60 years, which are based on the quantum theory. The small size of the printed circuit permits speed up, permits signals to be received and recognized at a much greater rate than was previously possible. So, for instance, electronic computers, which use transistors and similar gadgets very, very much. In the 1950s, when they first came on the market, then an electronic computer could make maybe 1,000 additions a second. I can make one. The present computers, however, can make 1 billion additions a second. So that made possible a tremendous increase in the power of computers. Now, in a computer, you have an operating part which actually performs the additions or multiplications, and you have a memory into which the computer stores much more information than it can keep in its operating part. And one of the problems which has slowed down computers is that it takes time to transfer data from the memory back into the operating part. Now, this is about to be accelerated very much from about 2 million transfers per second to 500 million, using a rather recent discovery made in 1980, the so-called quantum Hall effect. The inventor, Professor von Klitzing, was here to give lectures about 8 years ago, and I saw him a couple of weeks ago at Atlanta at a big meeting of the American Physical Society. So these are some of the inventions made on the basis of quantum theory. So quantum theory gave us both understanding of the way nature works and also technology. For me, the understanding is the most important. Now, unfortunately, much of quantum theory is mathematical. And I will try to reduce the mathematics to a minimum. Also, when I give you mathematical formulae, and I cannot avoid that, don't worry, you can understand the gist of the theory without understanding these formulae. I will not follow the historical development of quantum mechanics, but I'll present it the way that I think is more comprehensible. The first idea of quantum theory was introduced by Max Planck in 1900. Max Planck was was probably the most revered professor of physics in Germany, and has been honored after his death by giving his name to the most important research institutes throughout Germany. This was in 1900. The way he got to quantum theory was very indirect, and I must say that unfortunately many textbooks and many professors still guide their students to quantum theory the way Max Planck invented it. That's a very hard way to do it. A much easier way was found 5 years later by Einstein, who of course did a lot of other things beside. I never met Planck. I did meet Einstein after the war several times. We both worked together to try to reduce atomic weapons and try to prevent atomic war. Well, what did Einstein do? He used the photoelectric effect. It had been observed in 1887 by Heinrich Hertz that when you shine light on certain metals, then an electric current came out of the metal. And very soon thereafter it was found that this current consisted of electrons. The electron itself was discovered the same year, 1887, by J.J. Thomson. J.J. Thomson, I at least have seen in the flesh when I came to Cambridge in 1930, but Heinrich Hertz, unfortunately, I could not see, but he, of course, gave his name to the unit of frequency. You talk about electric light being 60 hertz, and when you take your radio, then radio signals go at thousands of hertz and so on. The most important feature of the photoelectric effect is that only ultraviolet light will produce the photoelectric effect. Ordinary light will not. Ultraviolet light means light of very high frequency, and if you want to know what frequency, the frequency is roughly 10 to the 15 hertz, meaning 1,000,000 billion oscillations per second. But that's irrelevant. Once you have high frequency, then the amount of electric current, the number of electrons which you get, is proportional to the intensity of the light. But when you use red light, nothing at all comes out of the metal. Well, knowing these facts, Einstein in 1905 took a leaf from Planck's discovery and said light consists of light quanta. It doesn't come out as a steady stream of radiation, but it comes out in single quanta. And each quantum has an energy of h times nu, where h is Planck's constant, and nu is the frequency of the light you are using, and that frequency in turn is the velocity of light, 300,000 kilometers per second, divided by the wavelength of light, which is something less than 1/10,000th of a centimeter. So you see, the frequency is very high, and Planck's constant is very small, and the product of that is the energy of one light quantum. So Einstein's was a direct way of getting to the idea of light quanta. The energy of the electron which comes out can be measured and is equal to the energy of the quantum minus a certain quantity, W, which is known as the work function of the metal, and which really means simply the energy necessary to liberate an electron from the metal. And that W is very small for alkali metals like sodium and potassium, and is very big for, let's say, silver or gold. The relation between electron energy and quantum energy holds not only for ultraviolet light, but also for X-rays, which are light of a much higher frequency, and then the electrons which can come out of metal when irradiated by X-rays are very high energy electrons, and conversely, you use high energy electrons which you direct against the metal in order to produce X-rays. So Einstein's relation is a very general one. Einstein's idea was revolutionary because everybody knew that light is really waves, oscillations in vacuum of the electromagnetic field. In fact, Heinrich Hertz, whom I mentioned before, was the first to put this fact into direct evidence. He made rapidly oscillating electric fields, and he thereby produced electric waves. And if he had lived a little later, he would have got the Nobel Prize, but unfortunately, he was dead by the time the prize was distributed. Well, light was known to be waves. That was known since about 1800, when Young demonstrated it experimentally. And everybody who had learned physics knew that light was waves. And now there comes Einstein and Planck telling you that it also is particles, quanta, and that somehow didn't connect with each other. It was a contradiction. So people in the early 1920s used to say, on Monday we believe that light are waves, and on Tuesday we believe that it's particles, and again the rest of the week. The matter was finally settled by A.H. Compton, who discovered a certain effect, namely when you put X-rays into some block of material and then observe the X-rays which come out of it. Those scattered X-rays have longer wavelengths and therefore a lower quantum energy. And the relation between the wavelength of the incoming X-rays and the scattered ones is exactly what you would expect if there was a collision between a light quantum and an electron, just like a collision between billiard balls. So that demonstrated that really light did consist of quanta. And after Compton's experiment in 1923, everybody believed that indeed light consists of quanta, but of course it also was waves. I knew A.H. Compton. He was at Chicago, chairman of the department. He was later on the director of the so-called metallurgical laboratory, which was part of the Manhattan Project, and which, under Fermi's direction, developed the chain reaction of uranium. Now, this contrast between wave and particle was finally put into a mathematical form by Dirac in 1926. That theory I'm not going to tell you because it is purely mathematical, but it reconciles the wave idea and the quantum idea for light. The Planck theory was confirmed experimentally and is now best confirmed by the cosmic background radiation, which comes to us all the time and which tells us something about the Big Bang, and it tells us that radiation in the universe was in equilibrium. In fact, 1 hour after the Big Bang, the world consisted mainly of radiation, and the radiation was in thermal equilibrium, and then the world expanded, as you know, and thereby the wavelength of each quantum became longer and longer, and thereby the energy of the quanta diminished, so that now the light, the quanta which are in the background radiation, are only a small part of the energy of the universe. But one can measure that background radiation very accurately, and this gives the distribution in frequency. The frequency is in cycles per centimeter, and this shows that this background radiation would be in equilibrium with matter at the temperature of 2.73 degrees absolute. And as you probably know, the energy, the temperature we live by, rather the temperature of melting ice, is 273 degrees absolute. So this is a beautiful curve, exactly confirming Planck's theory. My best friend in student days finished his studies in Berlin and attended the colloquium of the University of Berlin. At this university, at that time, 1928 or so, an experimenter found a curve like this by just looking at radiation which came from a black body. And now that had a much higher temperature, much higher frequency, but it had exactly the same curve. There was at the colloquium Professor Planck and also Professor Nernst, who didn't believe quantum theory. And when this curve was shown, Nernst got up and said, "Well, my dear colleague Planck, you still have a chance of being right." This was in 1928, when quantum theory was very well established. But Nernst still would not believe it because the most important theorem that he had invented could be explained by quantum theory, and he didn't like that. He wanted it to be known as the Nernst theorem. He had found it before quantum theory. Now, Einstein didn't rest. In 1917, he studied the equilibrium between light and matter, which was a purely abstract endeavor. And he concluded if you had a very strong beam of light, far stronger than anybody at that time could make, but as strong as the light which you have inside the sun. If you had such a stream of light, then that, and let it go through some material, liquid or solid or gas, and at any rate transparent, then this strong beam of light would stimulate atoms to emit more light of the same frequency exactly and in the same direction. And that is the basis of lasers. It was invented by a completely abstract argument by Einstein in 1917. Well, it took until the 1950s before lasers were actually made practical. There were 4 people mainly involved. Towns, whom I saw at that same meeting in Atlanta of the Physical Society. Charlo, who just died, and 2 Russians, Basov and Prokhorov. Well, all of them got the Nobel Prize for it. And it is an eminently practical discovery, practical invention, which is used to make very concentrated beams of light and to make heat sources which can penetrate deeply into matter. For instance, it was used already many, many years ago for operating on the retina of people's eyes, reattaching a retina which might have got loose. And this just to show how an abstract invention can be technically important. Well, now, however, let's go back to physics. The most important application of quantum theory was made by Niels Bohr in 1913. He was a Dane who was then 28 years old. He was a postdoc, and he wanted to get further information by going to England and studying with Ernest Rutherford, who had for many years studied the atomic nucleus. But what Bohr learned was not about the atomic nucleus, except that a nucleus exists. And Rutherford had made a model of an atom. He said there are lots of electrons in an atom. An electron has a charge -e, and they are held together by a nucleus which has a charge many times e, z times e. Z is always an integer. It's 1 for the hydrogen nucleus, it's 8 for the oxygen nucleus, and so for many others. And so Niels Bohr and Rutherford had said the electrons move like planets around the nucleus. Now Bohr took one relation from astronomy, so to speak, one relation which Newton, over 200 years earlier, knew already very well, namely, if a planet goes in a circle around the sun, the square of its velocity depends on the force, which in the case of an atom is proportional to, in the case of the hydrogen atom, is proportional to E squared divided by the mass of the planet or the electron and divided by the distance of the electron from the nucleus. So that Bohr took from Newton. But then Bohr added to it the postulate that the angular momentum of the electron, which is the product of its mass, its velocity, and its distance from the nucleus, should be equal to h times n being any integer, 1, 3, 7, whatever. And where this h is a little different from Planck's h, namely it's Planck's h divided by 2 pi, which is the ratio of the circumference of a circle to its radius. Well, Bohr I knew well. I met him in 1934, listened to him, and here is a picture of Bohr in a very typical attitude, namely lighting his pipe. He was forever lighting his pipe, and forever it went out. He was very tentative, not only in lighting his pipe, but also in speaking. Partly that is due to the Danish language, but he used it in Danish, English, German, whatever. And so when Bohr spoke, it was always rather difficult to follow him, especially when he came to to the real point of his sentence, he would drop his voice. And he often went to Princeton, to the Institute of Advanced Studies, and the secretary there took dictation from Bohr. The only way how she could do that was to take her pad and follow Bohr in his wanderings around the room. Otherwise, she would never be able to hear him. Well, Niels Bohr was a lovely person. He not only was a great physicist, in my opinion, as great as Einstein, and a very great teacher who taught dozens of young physicists, including many of my friends. But also he was a great human being. When Hitler sent so many German scholars out of the country, Bohr was very instrumental in giving them, in procuring positions for them. And later, when the atomic bomb was invented, Bohr did a lot of writing and speaking in favor of one world, in favor of an open world, in favor of a world without war. Bohr, from his postulates, could calculate the energy which an electron would have. Now, conventionally, one puts the energy of an electron far from the atom and at rest to zero. And since the nucleus attracts the electron, the energy of the electron in the atom is negative. Now, Bohr found that in the hydrogen atom, the energy is minus a certain constant divided by the square of an integer. And that constant he could calculate. It is called a Rydberg after a famous Swedish spectroscopist. This constant was related to the mass of the electron. It goes as the fourth power of the charge of the electron divided by 2 times h squared. Now, then Bohr made the further postulate. Electrons go around in one orbit of a certain n. Then when they want to emit light, they jump from a higher n to a lower n. And so he made the postulate that the energy of the quantum, which is then emitted, is just the difference between the energy they have initially and the energy they have afterwards. And that, when you use this formula, is this Rydberg constant times 1 over n squared minus 1 over m squared, these both being integers. Now, Bohr knew that such a formula had indeed been obtained from spectroscopy, from a measurement of the wavelength of light by a Basel physicist named Balmer in 1885, which happened to be the year Bohr was born. And Balmer had found this formula, which was well known to spectroscopists, and now Bohr had reproduced it, which was a tremendous success. to the wavelength of the light which comes out, well, if n is equal to 1, is about 100,000th of a centimeter. And a centimeter is about the width of a fingernail. So this was a complete confirmation of Bohr's ideas, so much and so astonishing that Rutherford said that now I believe my own model of the atom. Now you have proved it. Before that, he didn't believe his own theory. The Bohr-Balmer theory has been exactly confirmed by spectroscopy. You can measure the wavelength of spectral lines to a part in a million or better. So this is really a precise confirmation. And in addition, the formula for the Rydberg constant agrees exactly with the values of the constants involved, mass and electric charge and H, which at the time of Bohr were not terribly well known and now are very well known, and no matter how well you know them, they are, the agreement is exact. So Bohr's theory was an immediate success. Everybody was impressed of it. And it came even better. Namely, the next year, James Franck and Gustav Hertz did an experiment. I knew James Franck. I told you about the metallurgical laboratory of which Compton was the director. James Franck was the most distinguished scientist, chemist at that lab, and I knew him. Gustav Hertz was the nephew of Heinrich Hertz, who discovered the photoelectric effect. Well, they bombarded hydrogen atoms with electrons, and electrons, you can endow them with a well-defined energy, and as long as this energy was less than 10 electron volts, nothing happened to the hydrogen. But once you had more than 10 electron volts, the hydrogen would emit one spectral line, and then more spectral lines as you increase the energy, and when you put the energy up to 13.6 electron volts, which happens to be the Rydberg energy, then you could ionize the atoms, which means they could separate the electron from the nucleus. So this was a complete confirmation of Bohr's theory, just a year after the theory was published. It is interesting to calculate the radius of the innermost Bohr orbit, which is the one in which the electron normally sits. This is h squared over me squared. H again Planck's constant, mass of the electron and charge of the electron. And that is 1 centimeter divided by 200 million. So you see, the radius of the atom is much, much smaller than the wavelength of the light which the atom emits when it emits. And that shows that the light quantum can by no means be inside the hydrogen atom. It can only come out when the electron makes the transition from one quantum state to another. What the electron does when it emits light is to oscillate with a high frequency, and that frequency then is given to the light. The theory was further extended also in 1914 by Sommerfeld, who was my teacher. Sommerfeld said, and probably Bohr knew that already, that electrons, just like planets, don't have to go in circles, but they can also have elliptic orbits. And he classified the elliptic orbits by the eccentricity, by a certain number which is called L. L equal 0 means a very eccentric orbit that is essentially just oscillating in a straight line, up to n-1, n being that number which gives the energy of the orbit, and n-1 is a circle. For hydrogen, the difference in energy between these various elliptic orbits is very small, but for other atoms it becomes quite big, and so it is important to know about these ellipses. Sommerfeld was a Geheimrat, which was an honorary title given to very distinguished professors, and when he was sitting here, he obviously looked like a Geheimrat, and he also looked like the upper half of General Hindenburg, and he was quite short, and he was an inspired teacher who taught the majority of the theoretical physicists in Germany. So he completed the Bohr theory and also wrote wrote a book which made Bohr's theory more popular and extended it and drew many conclusions from it. And this is about where the theory was in 1915, and next time I will then tell you what happened to it later on.